What's up, guys and gals? Welcome to the LeetCode Larry Show. I am your host, LeetCode Larry, the only guy on the planet named LeetCode Larry whose name is not actually Larry. Today we're going to be looking at binary search. What's binary search? Binary search is a way to search through a sorted array. A sorted array. So, there are plenty of ways to search through a non-sorted sorted array, but there's plenty of ways to search through a sorted array. A linear search would do something like start at the beginning and just keep running through the array until you find the element. And what's the runtime of that? Well, it's going to be linear, and linear is good for a lot of things, but we can actually do better. We can do logarithmic time. We can do big O logarithm of n for binary search. How do we do that? Well, the key here, the reason it's called binary search is the way it's related to binary trees and binary search trees. Or, well, maybe it's the other way around. Maybe binary trees are actually related to the binary search. But the important thing is we can look at an element. Now, since we know this is sorted, how can we use that information to know where an element is? Well, if we look at the middle of the array, we see 5. We know that if we try to find an element, if we know 5 is greater than the element, then we know the element has to be on the left side of the array. But if we know 5 is less than the element, we know the element must be on the right side of the array. Or if 5 is the element, we know we found the element. So the key with binary search is, well, the problem, I guess I should have started, the problem we start with is, take a target, let's say 9. We need to find the index of the target in the array. This can come up in many applications, like database indexing, searching through, like a directory of addresses or phone numbers. Those are usually going to be sorted in some way. So it's better to use an algorithm like binary search or a variant of it than just using some linear scan. But this only works, as I said, if the input is sorted. So let's go ahead and work through the concept of binary search with this example. So what we're going to do is we're going to start with the middle element. We're going to look at the middle element. How do we calculate the middle here? Well, there's a few ways to do it. The easy way, and the way that's prone to overflow, but the easiest way, is to do left plus right over 2. Now we're going to start with left 0 and right, the length of the array. So 0, 1, 2, 3, 4, 5. So right now left is going to be equal to 0. And right is going to be equal to 5. It's really hard to draw on this. But, so the middle is going to be equal to, just call middle n. Middle is equal to 5 minus 0 over 2. Right minus left over 2. And we're going to truncate any decimal values. We're going to get 2. So where's 2 at here? It's 0, 1, 2. So we're actually using 3 as the middle. You can use, I guess, since a different way to calculate the middle, you could use 5, but here we're going to use 3 because there's an even number of elements here. Okay, we're going to use 3, and once we found this middle value, we're going to say 3 is the middle. We're going to look at the target value. In this case, it's 9. Is 3 less than, equal, or greater than 9? Well, 3 is less than 9. So we're actually going to break the problem down, and we're going to cut in half the problem here. This is what makes this a logarithmic time algorithm. We're actually getting rid of half of the input here. Now we know that this whole left side over here is just completely useless. We know that the target value is on the right side. We actually split the whole problem in half. So now we know that the target value is somewhere on the right side of this array. Now, what we can do here is we can update the left and the right index. So left is equal to 3. Right is equal to... Okay, so I should restate this. We're only going to update one index every time. So the right value is going to remain the same, right? Because the right value doesn't change. We're just shifting this over. We're shifting the left over 1. Because we know that everything to the left, L equals, so index 0, 1, and 2 do not include the target. We know that. So we shift left over 1. So we set left equal to middle plus 1. And right is going to stay as it was, 5. So now what do we have? Well, 3 plus 5 over 2 is going to be our new middle. So our middle, once again, is going to be left plus right over 2. So the middle here is going to be 4. What's the middle? Okay, so now we're looking at index 4. 9, is it less than, equal to, or greater? Okay, obviously it's equal to. So now once we've found the element that it's equal to, we return this index in the case of this. So we're solving. We look at the LeetCode problem here. I just started this video off talking about binary search, but binary search is actually a LeetCode problem here. We want to return the actual index of the integer. So we return the index. And here the index is 4. If, and in this case, they want us to return -1 if we never find the index. So that means if we keep searching, we search here, let's say we're looking for 13. What would we do? Well, we'd cut off even more of the input. We get to 12. And then what we do after we get to 12? Well, there's nothing else to cut off. So we're all out of ideas here. We're all out of options. We return -1. So that's the basic idea behind binary search. So let's look at the question real quick, and then let's go implement it in our little handy-dandy Google Docs. Given an array of integers nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If target exists, then return its index. Otherwise, return -1. You must write an algorithm with big O, log of n, runtime complexity. So like I said, this will work in log of n, logarithmic running time, because we split the input each time. We split this array up. We keep dividing it by 2 every time we make a comparison, which will be much quicker than a linear runtime or algorithm. So let's go ahead and code this up. So this is actually going to be an iterative solution. In the next video, I'll just make the recursive solution. Because I want to talk about how recursion plays into this in a different video. I don't want to make this about recursion right now, so we'll just do an iterative solution. So let's start by defining, what do we need to define? L and R, left and right. Left equals 0. Right equals length of nums minus 1. So now we have left equal to the very left of the array, index of the array. Right is equal to the very right of the index of the array. We're going to do while. So we're going to keep going until left and right are equal. So we're going to make sure we're doing this. So let's type this out. While left is left and are equal to right. So this loop will actually break and once left and right are equal, once we're only comparing one value. We want to do this because we want to make sure we actually check every value we can. Not every value in the array, but every value that will satisfy a certain condition. So, and if we don't find anything, we're going to return -1. So going back to this while loop here, this is where the crux of the logic is happening. So we're going to do middle is equal to left. Let's use some parentheses here just to make it more readable. Left plus right divided by 2. So middle, now we calculated the index of the middle value. Now what do we do with middle? Well, we want to compare it to the target. That's how this binary search works. So let's do this. If nums of middle, so the value of nums at index middle is equal to target, return middle. So we return the index who actually found the target. Else, what do we want to do? So like I said before, when we were looking for 9, the middle was 3. So let's do else if actually. Let's go with one condition here. Let's do if middle is less than target. So in this condition, what did we do? So middle was equal to 2, the nums of middle was equal to 3. The value is 3. So what do we do here? We know that the value at the index middle is actually less than the target. So that means we can actually get rid of this whole, we can stop looking at this array here, and we can just update our left index to point to middle plus 1. So there we do middle plus or equal to, oh, okay, I'm sorry, that's not right. Left is equal to middle plus 1. We don't increment middle here. So yeah, in this case, like we just moved left up 1. So left is 3 and right can say to be 5. Now let's take another example. Let's say the value was 0. So let's say the target was 0. Now once again our middle was here at 2, pointing to the value of 3. What would we do? Well, we know that 3 is greater than 0. So we know that else, we can just do else here. The only other alternative is middle being greater than 0, greater than the target. So middle is greater than the target. We can actually get rid of everything on the right side of the array. We can stop, I shouldn't say we get rid of. We stop looking at values on the right side of the array because we don't care about them anymore. We know they couldn't possibly be the answer. Because this is a sorted array, so we know if 3 is greater than the target, then we know it has to be on this left side. So we're actually going to update the right index in this case. So in this case, we would update right equal to middle minus 1. So we would just have left equals 0 and right equals 1 if we were to do this. So we do right equals middle minus 1. And that's pretty much it. That's the whole crux of the binary search algorithm. So that's everything. We just use these two indexes, left and right, and we have a while loop. Like I said, we're doing it iteratively in this video, but we'll do it recursively in the next one. Recursively, I don't know, it's hard to say which is better. That's more of a philosophical debate. I guess iteratively doesn't use the extra memory of the call stacks. So I guess iteratively is the preferred solution in practice. But I guess that's more of a philosophical debate we don't need to do in this video. But since we're doing it iteratively, we're just using this while loop, and we're going to keep looping until this condition is satisfied. While this condition is satisfied. And once this condition is satisfied for the last time, that means we've looked at all the possible values. And if we can't find anything, we just return -1. So let's go ahead and move from our Google Doc to LeetCode, our favorite website. And I already ran this as a practice round a little bit before this video. So let's go ahead and submit and see what we get. No, I got it wrong. Where did I make an error here? Right equals length of nums minus 1. If nums the middle equals target, return the middle. Else middle is less than target. I think of middle plus 1. Oh, so here I made a mistake. Here I was comparing else the middle is less than target, but we actually want to compare nums of middle. So what was my mistake? I was comparing the index to the target. So what I should have been doing is comparing the value at the index to the target. So I should, like if we're looking at this index here, this is the middle. When the index of middle is 2, but that's not important. What's important is the value must be what the value is compared to the target. So I forgot that I accidentally just wrote middle when it should have been nums of middle. But now, as we see, it works. And that's it. That's the gist of binary search. You know, maybe in the next video we'll go over the recursive solution, and maybe in another video we'll go over, the theory of logarithmic runtime and how it's related to binary search trees. Why logarithmic runtime is so much better than linear runtime. And why even this algorithm? I think I kind of explained why this is logarithmic, but I think I could go into a lot more depth, maybe more theoretical lecture on that. But that's it. That's the gist of binary search. And once again, this was the LeetCode Larry show. I am LeetCode Larry, the only guy on the planet named LeetCode Larry, whose name is not actually Larry. Ciao.